Well, welcome to your third lesson of your spring break. Hooray! Okay, this is board problem 37. Which of the following variables is a continuous variable? The lifetime of a 9-volt battery, the number of cracked eggs in a carton of 12 eggs, the number of people in a family, the brand of laundry detergent, and the number of students in your AP Stat class. Okay, continuous means you can't count it. A discrete random variable is something countable. So a carton of eggs of 12, that's countable. The number of people in your family, that's countable. The brand of laundry detergent, although that's not countable, that's not it right there. It's this one right here. I can't count the lifetime of a 9-volt battery right there. It's just an interval that I can't count, so it's going to be choice A. Okay, so they're just not countable. All right, let's begin. This is means and variance of random variables. The mean, and we're going to just start right into some examples, you guys. The mean of a tri-state pick, 3 playoff, and this is example 7.5 on page 407. Most states and Canada provinces have a government-sponsored lottery, just like we have a lottery in California. In this one, though, this is a simple, it's called the Tri-State Pick 3 game that New Hampshire shares with Maine and Vermont. You choose 3-digit numbers, and the state chooses a 3-digit winning number at random and pays you $500 if your number is chosen. Sounds pretty good. Because there are 1,000 entries, then you have the probability of 1/1000th of winning, right? Okay, because 1,000 entries, 3-digit numbers, so that makes 1,000, 000 all the way up through 999. It's 1,000 numbers. So here's the payoff, you guys. So the payoff is $0 999 times out of 1,000. You would win $0 in the long run. You could get lucky, but the payoff in the long run. And the payoff for a $500 one is 0.001, which is 1 in 1,000. Okay, makes sense? Yes. All right, so what is your average payoff from the many tickets? Okay, this is from many tickets. So the ordinary average of, and this is after you pay, the ordinary average of the two possible outcomes, $0 and $500, is 250, right? If you average these two numbers, 0 and 500, it would be 250. But that makes no sense in the averaging because the 500 is much less likely than the 0. There's more times you're going to win. There's 999 more times you're going to win 0. So in the long run, you receive $500 once in every 1,000 tickets that you buy, and the remaining 999 tickets you lose. Okay, so here's the long run payoff average. $500 times 1/1000th, and then $0 times 99 1,000ths, and it ends up being 50 cents. So every dollar that you pay in the long run, you get 50 cents back. Hooray! The number is the mean of the random variable. Tickets cost you $1, so in the long run you get 50 cents back. In other words, the state makes 50 cents off your bet. Okay, they say that the lottery is a tax on people that don't understand math, although I still play it every now and then, especially when it gets big. Let's see, the mean or a discrete random variable. Okay, let's see, suppose that x is a discrete random variable. Remember, discrete random means something that you can count. With this distribution, okay, so you have this x and it has this probability, and your second x has the second probability, and so all your x's have their shared probabilities. Okay, to find the mean of these, you multiply all the possible outcomes and then add them all together. So I'm going to go x sub 1 times p sub 1 plus x sub 2 times p sub 2 plus x sub 3 times p sub 3, all the way from x sub k to p sub k. Okay, so there it is right there. And that's what that says. And remember summation notation from your Algebra 2 class. So this just says x sub I, p, and so just add them all up. It's just this shortcut for writing that right there, okay? All right, don't worry about that formula too much. Just the one above it's better. Okay, random digits compared with Benford's law. Okay, so remember random digits? So this is example 7.6 on pages 408 and 409. Random digits, if they were just random, not Benford's digits, but random digits, 1 through 9, they all have the same probability of 1/9. Remember that? Okay, all these digits have 1/9 of a chance to be randomly picked. So if we found the mean of those, we just go, the 1 times 1/9, 2 times 1/9, 3 times 1/9, and so on and so on and so on. And then what your book did is they GCF'd out the 1/9, and I think I did it on the next slide. Let's see. Yeah, I did. If you can see the small writing, they pulled the 1/9 out because they all had the 1/9 in common right there. So they yanked that out, and you're left with 1 plus 2 plus 3 plus all the way up to 9. That equals 45. So that's that mess right there. So 1/9 of 45 is equal to 5. Okay, so the mean of those numbers is 5. Okay, but on the other hand, Benford's law, remember the first digit was different. The first digit had a higher priority than the second digit, and all the way down. I mean, look at the probability of digit number 9 right there. So when you found the mean of that, you guys, they did this number times this number plus, whoops, I did it again, this number times this number, and so on all the way through. And they got 0.344, not 5, what we got on the last time. So the higher probability of the lower numbers was reflected. This had a higher probability, so it pulled the mean down. Okay, makes sense? So I'm going to show you a graph of these. So here is the graph of the 1/9, the 1/9, the 1/9, okay? These all had 1/9 of a chance. 1/9 is 0.111, and all these bars are right above about 0.111. So the mean was right there in the middle at 0.5 right there, or at 5, okay? That's the mean right there, okay? But Benford's law was 0.344. So here's Benford's law right there. You had to calculate that baby out. So 0.344. Remember, here's 3 right here where my cursor is. 4 is right here. So this is about 0.344 or something like that. Okay? All right, so easy, huh? You're just finding the mean of those. So the variance of a discrete random variable, suppose that x is a discrete random variable whose distribution, just like before, is this. Okay, first you got to find the mean. Okay, so and once you find the mean, which we just did in those prior examples, then the variance is we're going to take each number and subtract the mean and square it. Okay, so look, you guys, this is variance. This is mean variance, and we did this before also. So we do each number minus the mean squared, and then multiply it times the probability, plus the second number minus the mean squared times its probability, all the way to the last number minus the mean squared times the last number's probability. Okay, and then you add them all up. That's the variance. Okay, and then the standard deviation is just the square root of the variance. Okay, it's just other ways to calculate standard deviations and variance. All right, so selling aircraft parts. So this is example 7.7 on page 411. Okay, so this just talks about some aircraft parts that they're doing right here, and I'm just going to jump to save some time right here. So the units sold, they got 1,000 units sold, and the probability are these. So 3,000 units sold, and the probability, and 5,000 and this probability, and so on. So first we got to calculate the average, you guys. So we're going to go through and find the mean, you guys. So we're going to go this times this plus this times this and add them all up, so we get 5,000 units is the mean. Okay. And then to find the variance, you guys, we do each number minus the mean squared. So it's the first number minus the mean squared times the first one's probability, the second number minus the mean squared times the second one's probability, and so on and so on and so on, okay, all the way to the last one. So when we get that, you add them all up and you get 7,800,000, and then you square root that, and then that's your standard deviation.